Hi everyone, and thanks for joining us today in this, which is the third in our series of webinars for 2018, which discusses LimitState products, their features and their applications. I'm Tom Pritchard, I'm the host for today's event, and I'll be introducing the webinar and also rounding up at the end. Today's webinar is entitled Make More Informed Masonry Arch Bridge Assessments with LimitState Ring, and it's going to provide you all with an overview of LimitState Ring, our masonry arch analysis software, what it does and how to use it. The main part of the webinar itself will run until approximately 1:10 p.m. UK time and will include 5 or 10 minutes at the end for questions. We can always post these via the question functionality that should be present in the webinar interface in front of you, and we do try to answer as many of them as we can during the time available. Occasionally we don't get a chance to go through all of them. I do apologise in advance if that happens today, because there are quite a few of you online today, but we will try and reply to everybody after the webinar has ended if we don't manage to get round to them. We do have a mixed audience today. Some of you will have used LimitState Ring before and some of you will be completely new to it. For anybody who has used it before and has specific questions regarding the software, please consider also contacting us outside the webinar via info@limitstate.com, and we'll be happy to answer detailed questions for you that way. So our speaker today is Matthew Gilbert, who is the LimitState Ring product manager, and I'll pass you over to him.
Thanks very much, Tom, and thanks very much to everyone for joining us for the webinar today. Okay, so just a quick look at what we're going to be covering in today's webinar. First of all, I'll say a few words about LimitState, the company, then move on to talk about some of the fundamentals, sort of ways in which masonry arch bridges work, carry load, etc. Then have a look at how we use the software to analyse masonry arch bridges, for moving on to an example, which today is going to be a twin span highway bridge, and wrap up with some conclusions, and then I'll pass back over to Tom to handle the questions. Okay, so first of all, just a few words about LimitState. We set up actually just over 10 years ago to provide engineers with powerful software, particularly focusing on the ultimate limit state for analysis and design purposes. And what we do is we apply optimization algorithms and associated technology which are not used by normal mainstream analysis tools. As a company, we committed to ensuring the software is robust, well validated, and also well supported. So large number of users in around 30 countries worldwide. We've got a small number of those shown on screen, as you can see. In terms of where we fit in the landscape of software, hand analysis and other tools, what we try and do is fit between hand calculations at one extreme and sort of simplified automatic hand calculations, perhaps embedded in spreadsheets and the like, and at the other extreme, high-end analysis tools, for example, non-linear finite elements, discrete element method and so forth. So we sit between those. We're trying to effectively provide the sort of the speed and convenience of traditional tools, but with a good deal of the power associated with the more advanced tools. So in other words, we can, for example, modify local properties, see how that affects the performance and so forth. And so the idea is you can quickly get solutions as opposed to waiting often considerable time with advanced tools, and also with a requirement for quite a lot of expertise in the latter case. So obviously you do need to know what you're doing when you're using our tools, as with all tools. However, the learning curve is much less steep. Okay, so moving on to the main content of the webinar. Fundamentals of masonry arch bridge analysis is something that clearly you all will be interested in. First thing to say is there are an awful lot of masonry arch bridges out there. We think there are around 1 million spans worldwide, concentrated particularly in Western Europe, but also in a number of other places around the world. Most of them are at least 100 years old, many much older than that, and we need to make sure that we assess these to confirm that they're adequate for carrying current and proposed new traffic loadings. In terms of terminology, masonry arch bridges are not covered on the syllabuses of many university courses, so there's a little bit of a kind of a learning curve to get up to speed. I'm not going to go into too many obscure details, but just to say that an arch barrel is made up of arch rings, which spans from springings. Above the arch barrel, you have the spandrel region, which might comprise internal walls or solid masonry or concrete backing, or very often backfill material. Typically you have spandrel walls at the edges of the bridge. In terms of the arch barrel, then this can be formed in masonry, stone masonry, in which case we have large voussoirs, but if it's brickwork, we might have a number of separate rings of brickwork forming the arch barrel. I'm going to sort of briefly look at how these structures work, because clearly they don't work in the same way as a traditional beam, for example. And we know that masonry is very good at carrying compressive loads. It's much less able to carry tension loads. So probably the most sort of fundamental bit of theory that was developed for masonry arches came from Robert Hooke several hundred years ago. He encoded in an anagram, actually, as hangs the a weightless chain, so but inverted, stands the masonry arch. What did he mean by that? If you get all the voussoirs that you're going to use to form your masonry arch, you suspend them from a weightless hanging chain or cable. You look at the profile that chain or cable takes up. You invert that, and you find that you can fit that entirely within the thickness of the masonry. Then you know that your arch should stand when you remove the formwork. So there's a red profile that we call the line of thrust or line of compression, but this is a statically indeterminate structure, so there are actually other possible lines of thrust, and we don't know in advance which of those is going to be active at any particular time. However, when we apply, for example, an eccentric load to our masonry arch, and we keep increasing that, we'll come to a point at which we can only just fit that line of thrust within the thickness of the masonry. And at that point, if we try and apply any more load, we will actually get hinges forming, and we will get collapse. Now that state is actually well defined, so we can use analysis tools to quite easily and quickly identify that situation, and that's what we do with the LimitState ring software, as we'll see later. The other thing to note at this point is the shape of the arch in relation to the pattern of loading that governs stability. So that means it's important when you're doing your assessment to carefully measure the shape of the arch profile, and also likewise have a look at the pattern of loading that your traffic is applying. Particularly, for example, on the railways, we might have a transition from short wheelbase wagons to long wheelbase wagons, which can have a very different effect on the masonry arch bridges that they're crossing, even if the axle loads are much the same. The other thing I've not mentioned is An arch bridge is much more than an arch barrel. We also have fill surrounding the arch barrel, and that helps provide additional reserves of strength. What we are also going to focus on today is the ultimate limit state, and we're assuming implicitly that the serviceability limit state is implicitly satisfied. Now actually we're looking at this in quite a lot of detail, and hopefully in the quite near future we'll be able to talk a little bit more about how we can use a tool like limit state ring to also do an explicit serviceability limit state type check. So just to summarize methods that are available for masonry arch bridges. The hand type calculation, probably the most common example of that is the so-called Mexi method, developed in the Second World War as a quick way of allowing the army to check the capacity of bridges under the action of military loading. And then at the other end of the spectrum we've got finite elements or discrete elements. So we sit in the middle. Limit state ring is a limit analysis method, and we can simultaneously actually look at the line of thrust, but also the mechanism of failure, as we'll see. What's kind of obvious is there's a sort of a continuum between the hand calculation and the non-linear stiffness-based methods, etc., in terms of complexity and expertise required. So let's have a look at how we can use limit state ring in anger to analyze masonry arch bridges. Mentioned a little bit of this already. First of all, what does limit state ring do? What makes it different from other tools? Well, what we're doing is we're using optimization techniques actually to find in a rigorous way the mechanism collapse and the associated line of thrust at that point. It was actually developed, oh, this is scary, about 25 years ago, the first version. And it was actually developed as a means of understanding laboratory test results, and ever since then it's been validated against results as they come through. And lastly, the user interface that's been developed in recent years has been designed to do two things really. One is to allow users to very quickly get an estimate, a rough estimate of the capacity of a bridge. And the second way of using it is to also allow users to perform a more detailed analysis using local knowledge of what the local defects and local properties are of the structure. So if we look at the first mode, so the quick assessment, we have got a wizard that we can work through to quickly set up the properties. And the second mode, we can, for example, enter in details of local mortar loss, see whether or not mortar loss is having a critical influence on the behavior of the structure, or whether it's something that you know, can be put off a little longer before we go to the expense of dealing with it. So for example here, what we've done is, for example, for a bridge over a stream where perhaps we've got washout of mortar near the abutments, we've actually removed mortar, and what we're going to do is see how that influences the mode of response. Okay, so what I'm going to do is actually I'll quickly look a little bit more how it works, and then I'll open the software and kind of and show you what it does. So how does it work? The load from vehicles is dispersed through the fill onto blocks, which are actually separated by contacts, which is actually where the interesting stuff happens. We model the crushing sliding and hinging behaviour there. We also then have the ability to model one of the effects of the, or two of the effects of the backfill. So in total, we set back, there's 3 effects of backfill. One is dispersion of that live load through the backfill. The second is the simple self-weight of the backfill, acting to pre-stress the arch barrel. And the third effect you can see on screen now are these backfill elements, which are actually providing passive restraint to the arch. And in terms of the objects on screen, you can see here we've got hinges, a line or zone of thrust, we've got the backfill elements, and you can see basically the key elements there now. But what I'll do is I'll just start the software and actually hopefully bring it to life a bit more. So what I'm going to do is use the new bridge wizard to just set up a simple example bridge, and then have a look at, for example, assigning some local properties. So in terms of the new bridge wizard, this is an opportunity to basically describe the bridge, say whether it's a highway bridge or a railway bridge. If it's a railway bridge, then we have access to standard railway vehicles, and also we take account of distribution through the track and sleepers. If we move on through the wizard, then we've got an opportunity to describe the geometry. So initially we can have a description of the end abutment blocks. Generally this is suitable when you don't have soil behind the abutment, because normally the expectation in that case is that you have essentially rigid abutments. But if you have end standing abutments, you can describe those explicitly here. You can also specify whether there's some backing, for example concrete backing, above the abutment. Then move on to define the geometry of the arch barrel of span 1, and we've got various options. We can describe a voussoir arch, a bonded brick arch, or a multi-ring arch where those rings have become debonded. And also we can describe the shape of the structure either in a simplified way, where we're assuming it's segmental as of now, or we can specify various user-defined shapes, and also another couple of built-in ones, a pointed arch and a free-centered arch. What I'll do now, however, is keep the defaults just for simplicity, but I will add an extra span. So when I go next, I'm then asked to provide details of the pier that's adjoined span 1. I'll change the height, for example, to 2.5 meters. I'll keep the thickness the same, but obviously in reality you would enter the details of your bridge that you're looking at. If I click next and come back to the next span, I can add as many spans as I want. I'll keep it probably at 2 spans for simplicity, and then move on to the other end abutment, which again I'll skip through. The next part of the geometry relates to the fill. How much fill is there? And also it splits the fill into near surface fill and fill lower down. We can actually ascribe different properties to surface fill if we want. And here I've got actually 500 millimeters of surface fill as a default. Move on. We can enter partial factors. So if we're doing an assessment to a code of practice, and actually an example that we're going to look at a little bit later, we'll do that. You can enter the details here. If you are working on a sort of traditional approach where you're looking for a global factor of safety, you can just keep it as unity for the time being. But you can see you can apply partial factors to loads and also to material properties. If we move on to the materials, then what I can do is describe the properties of the masonry. So unit weight, crushing, friction are all possible to define. I can also, as well as having a global set of properties, I can actually split and have separate properties for the spans and for the piers, as you can see. And also I could actually separate it for all different areas of the bridge if I wanted, so the abutments, skew backs and spans and so on. However, for this simple example, I'm going to keep things global. So we've got a global unit weight and crushing strength. Now, the crushing strength, the default crushing strength is 5 newtons per millimeter squared, which is quite a conservative value. And similarly, angle of friction that's shown there is a reasonable but reasonably conservative value. So the idea is that if you don't know at this point what these properties are, you can use the default values and get a good idea for the likely load carrying capacity of your bridge. Moving on, the backfill. But basically got a standard geotechnical properties, so unit weight, angle of friction and cohesion. And also a couple of tick boxes to effectively allow us to either model the effects that I mentioned earlier of dispersion of the live load and passive pressures. If we switch those off, then clearly we will reduce the effect of the soil and reduce the load carrying capacity of the structure. One thing to note is that the soil is not modeled explicitly in the software. It's the anticipated effects of the soil that are modeled. And then move on, surface fill. As I mentioned, we can have a different unit weight for the surface fill, and we can also have a different angle of spread of the live load. Move on then to the loads. By default, we have a single axle, 1 kilonewton single axle load. But if I go to my vehicle database, there are actually lots of built-in vehicles, and I can, for example, import a vehicle from that database. And I can make use of that. And I can finish. There is the vehicle on the bridge. So now I've got my bridge set up. I click the green button here. I solve, and I can get a result pretty much instantly. And you can see some of these features that we saw earlier. So the hinges, the thrust line, which is actually a thrust zone, where the thickness is a function of the amount of material, amount of thickness of masonry required to carry the load. And also we can see these backfill elements which are representing passive resistance. And you can see we've got that at the end. We've also got it over the pier as well. What we've actually got shown in the console window is an adequacy factor. This is actually a multiplier on the applied load. Because I had no partial factors, then this is actually a factor of safety. So it's a load factor basically. What I can do is I can just drag the vehicle and we can explore different modes of response. and also have a look at different adequacy factors. So we can very quickly and easily get a feeling for how sensitive the bridge is to position. And we can see that, you know, probably the adequacy factor for this bridge is about 3.5. With a mechanism involving berth spans. What I can also do, however, as I mentioned before, is I can specify local properties. So what I can do is zoom in, and for example, I can put in mortar loss of, I don't know, 100 millimeters. Actually put it on both sides. So let's suppose that this pier is sitting in a river and we've got washout. And if I click solve, then we can see actually that influences the mode of response, and it actually reduces the adequacy factor from about 3.5 down to 3.24, assuming that the load is in this position. Obviously, I would then also potentially need to try different loading positions. But basically, hopefully gives you a quick idea that you can set up a problem quickly and easily using the wizard, but you can then also zoom in and change things. Okay, so going back to the presentation, the question is, how do we get these results in terms of the maths? Basically, for every block, we're looking at equilibrium. So here's a block that's pulled out of my bridge. We also have yield, and this is actually dealt with in the contacts. So for equilibrium, every block has a self-weight load, but also forces coming at the contacts. But we can also provide limits on those interface or contact forces. So for example, to say that we potentially could have sliding. So we have the shear force. The limit is between the coefficient of friction times the normal force in one direction and also in the other direction. And similarly, we can have rocking failure with the relation above. And it's a nice, simple, quick to solve problem. So this is just a few slides to show you how we validate the results. This is one of the bridges that was tested back in the 1990s that accompanied the original development of software. So this is a 5-meter span bridge, overall length 40 meters, lots of instrumentation. We also carried out tests on multi-span bridges at the time, and you can see the results from a very early version of the software above. And more recently, we've been looking at soil arch interaction in a bit more detail, and we've actually got here shown on screen a bridge that's been constructed in effectively a large fish tank. This is a 3-meter span arch in about an 8.5 meter long fish tank, and you can use digital imaging techniques to actually track how that film moves around relative to the arch under the when an arch bridge is loaded. And actually, we've also done some very small scale tests where we've been able to actually decouple or isolate individual effects of the soil and validate the software that way. So for example, remove the live load spreading or remove the passive resistance. And in all cases, we got within about 10% of the predicted results, which was very, very positive outcome. Okay, so I've talked a little bit about the background of masonry arch bridges, how the software works. Let's have a look now at a practical example. In this case, it's a twin span highway bridge. It's actually, you can see it's a pretty modest structure, 2.7 meter spans, and a 700 millimeter thick intermediate pier. Also, you can see we've got 2 rings of brickwork forming the structure. Now, what I would say is, although it's quite a modest span, one of the issues with a masonry arch is that if you have a very long span masonry arch, then live load in relation to the self-weight is small, and actually you're likely to have a very high load carrying capacity. It's often at the low end of the scale, smaller structures where live loads are actually quite significant in relation to self-weight, that you get more problems. Okay, so moving to a photograph, you can see here again a little bit more about the bridge. Soft red clay bricks, and you can see these two rings of brickwork. Can't see that well, but the profile is actually somewhat distorted, put it that way. And actually what I've got is a if I just go back to the software, I have this bridge actually brought in. Initially, we've neglected the fact that it's multi-ring here, so we've actually assumed that it's effectively acting as a voussoir arch, but we've built in the slightly distorted profile. And the way we've done that, if we go to the span tab, we actually assumed that this is a user-defined shape, and we're using the spline interpolated profile, and we're entering in 9 different measurements to represent the arch in that case. Another thing that we've done here, which I mentioned earlier we would do, is if we go to the vehicle, we've actually got an 11.5 ton single axle, which is one of the scenarios that we consider in the UK, and also now we've got a dynamic factor applied to the axle. If I go to the partial factors tab, you can see we've actually got then the value of the dynamic factor applied is 1.8. We've also got an axle factor of 1.9. Actually 1.9 times 1.8 equals 3.4, which those in the UK will be very familiar with. So in this case, we've got the vehicle load as represented by a single axle, and we've also factoring that up. So when I click solve, the adequacy factor that I get in the console output window is now effectively a factor on a factor. So in design we might call it an over-design factor. In assessment we call it an adequacy factor. So in other words, if that's at least 1, then we have a safe situation. If it's less than 1, it means that the loading that you've applied is too great for the structure. So in terms of the this bridge, I can do what I was doing before and play around with the location of the axle, but also, and sometimes more convenient, I can, if I want to, I can actually indicate that the vehicle is going to traverse the structure in increments. So what I can do is I can copy that first load and load case, and I can put maybe a total of 30 load cases, and I can move each load relative to the last one by, say, 200 millimeters. So if I do that, and I can go, I can then actually see that I've got lots of load cases, and each load case is moving the vehicle across the structure. And now if I click solve, what it's actually doing is moving that vehicle or single axle across the structure, and it's trying to find the critical one. And what it's actually found is that in this case, load case 24 is critical, where the adequacy factor was 1.0272. So actually very close to 1, but just above 1. That's okay. However, I did mention earlier on that this is a multi-ring structure, and I haven't represented that in the analysis. So what I could do, if I go back to the span, is I could change this to be a multi-ring arch, and if I change this, instead of comprising one arch barrel that's 220 fig, I could have it as 2 rings each 110. I'll do the same for both of those spans. And I click OK, and now you can see we're now modelling the worst case scenario actually, where this is 2 rings of brickwork with frictional interfaces between each of those rings. If I click solve, again we're going to do the traverse across the bridge. It's taking a slightly longer to solve. In this case, the same load case is critical, load case 24, but you can see actually the adequacy factor is much lower. It's gone down from about 1 to 0.527. So clearly, if we have full ring separation, then we have potentially significantly lower capacity. But you can see it's very easy with the software to model this, and also we have not got time to talk about it now. Potentially, you can also model partial ring separation scenarios. So what we can do is simply model ring separation, for example, in the crown region, depending on what the outcome of your survey has been. Okay, so the other thing you might be asking, this is an adequacy factor of 0.527. What does that actually mean in terms of what vehicle can cross the structure? If you work in the UK, then if you go to the LimitState website, you can see documentation. There is actually a little application note which tells you that if you have an adequacy on an 11.5 ton single axle of, in this case, at least 0.47, then the maximum gross vehicle weight is 7.5 tons. So it might be that you want to consider, if you feel this is a true representation of your bridge, then you can obviously consider imposing a weight restriction prior to, for example, undertaking some improvement program. Okay, so moving then on to conclusions. Just got time to bring up a few key points. First one, shape of the arch in relation to the pattern of loading is important. If you try the software, you can see that very clearly, and any sensible masonry arch analysis program should tell you the same. It's just to identify here when you're doing a site investigation, when you're looking at geometrical measurements, do take the time to measure the arch profile sensibly, and also consider what pattern of loading your structure is likely to be subjected to. So LimitState Ring is a rapid and powerful analysis tool. You can automatically identify many modes of failure, so the multi-span failure mechanisms you can identify directly. There's no need to manually balance thrusts at pier heads or anything like that. You can directly identify modes of failure, and also that can encompass sliding failure, multi-ring failure. And then lastly, I mentioned it earlier on, there's 2 key ways of using the software. One, using default parameters for a quick assessment, and secondly, using taking advantage of the ability to model local features of the software. Okay, so that's all I'm going to say. I'm going to hand you back now to Tom, who's going to pick up on the questions.
Thanks, Matthew. So yeah, if people do have any questions, then please feel free to stick them into the question functionality now, and I'll be able to take any that you give. Okay, so the first one is, does the software have inbuilt load models for highways and for railways in the UK? Yes, that is yes. So I'll just see if there's a copy open.
I think I mentioned that earlier, but anyway, Tom can actually prove it in.
So if I drag this across, we can see if I go for a new file here, you can change the bridge type to highway or railway. So if I say railway and just finish, you can see we've got a railway on the top there. And then if I go into the loading dialog and the vehicle database, we can see that we have different vehicles there. And I'll just leave it on this single axle here, and you can also see that the loading is spread out through the rails accordingly, but you can put your own railway or highway vehicle loading in there as well, as actually choose from the ones that are available within the software. So does the software calculate resultant thrust on the piers or the abutments? So if I just go back to the front view and turn it off 3D and solve, what we can see here is that we've got the thrust line, and if I click on this contact surface here in the property editor on the right hand side, you can see what the normal force and the shear forces are on that particular contact. If you wanted a better overview of the forces on all of the contacts, then you can click one of these orange icons on the left hand side here, and we can see in this case what the moment is, or what the normal force, or what the shear force is moving from one side of the bridge to the other. There's a question, can you apply settlement? So if we have a look, what we can do is change the type of analysis to a support movement analysis, and in this case we can pick a support block, say this one on the right hand side here, and move it down by a set distance. Click OK, and then when I solve the problem here, what you'll see is if I make the animation slightly higher, that this support here on the right hand side is moving down, and we can see what the thrust line and the failure mechanism is like in that case. And there's actually a separate webinar that deals with this type of thing in a little more detail on our YouTube channel, which I'll send a link out with the email that goes out after this webinar, so people can look at that if they wish. So time's pretty much up now, so I'd just like to thank Matthew again and thank everybody here for listening today. We hope you found the webinar informative, and that it's hopefully given you a better idea of what the capabilities of LimitState Ring are. For people who are current users of the software, then yeah, obviously hope you learned something new. If you have any questions, then please do get in touch with us. Everyone probably also interested to know that there'll be some forthcoming webinars that deal with both LimitState Ring in more detail, and some of the different functions and features of it, and some of our other bits of software, so LimitState Geo, LimitState Slab, etc., for the rest of the year. So please look out for the event notifications that we'll send out via email, and also post on our website at limitstate.com/events. So finally, I'd just like to say thank you all again for listening, and hope you can join us again for one of those future sessions. Goodbye.